I'll just be giving the second part of the complexity thing on probabilistically checkable proofs. I understand it's a complexity thing doing interactive proofs, essentially the proof of IP equals P space in the morning, followed by PCPs in the afternoon. It's very heavy, so let's make it as interactive as possible. Ask me as many questions as possible so that I don't cheat and throw things under the rug as it goes on. So the plan for this one is going to sort of give an outline of what proofs are, verification, make a gradual introduction and define what PCPs sort of proofs that allow for super fast verification. We will then see the statement of the PCP theorem, discuss sort of implications of it, what it means in our context of fast verification. And then, having spent about 30-40 minutes on this, the remaining sort of amount of time, I'll try to give a bird's eye overview of the PCP construction. How does one construct such proofs that are extremely fast, verifiable and extremely efficiently? And depending on how much time I have later on towards the end, we'll talk about even making the verification even sublinear time, not just efficient. Okay. Let's get started. So what did we see in the morning? We saw in the morning of this sort of thing in which there is a sort of a weak sort of computational model which client which wants to perform some task T, or say it wants to find out if some statement which I'll call a theorem T is true or false. It takes the help of a very powerful, a computationally powerful server which accomplishes the task or proves or says whether the task T or say proves the theorem, says yes or true or false for the theorem statement. But the weak model does not trust the server, so they then had a conversation back and forth, of course, in the form of challenges and responses. At the end of which the client sort of either accepts or rejects. And the important point over here is we allowed sort of interaction, and we allowed the client to toss random coins to make the check. That was important. The fact that the what was called verifier, this was called verifier in the morning, and this is what was called prover. So we allowed two, from our usual notion of verification, we had two extra features. One is the feature of interaction, that is, you're allowed to ask questions back and forth with the prover. And second thing is, these questions are sort of randomly generated, and it was important to have this randomness. We saw that in some of the cases, randomness really gave you the extra power. But not always do we have the pleasure of having to be able to ask this extra prover these challenges in response. For example, you get to know that the prover tells you the answer, and then you want to somehow check it later on if this task has actually been accomplished or true or false. So you don't necessarily interaction is not always feasible. Not always feasible. This could also be just because it's not one single entity that's computing the accomplishing task. It's a distributed entity, and it's hard to. Its interaction is an expense of this one. So, what you expect in such cases is actually the prover not just instead of interacting with you, sort of gives you out something. It publishes a proof, which you could sort of check to see. Instead of interaction, the prover provides a proof that allows the verifier to do whatever was done over here, to check if task was performed successfully, or theorem was Of course, once we come to this model, we are going to the classical model of NP, in which there is some statement that the verifier wants to check. It's just the prover, the all-powerful prover, is trying to perform this task, and then at the end of it, not just perform the task, it gives out a proof stating that the task has been performed. Thus, we are going into the classical definition of NP. Of course, you could, because we are also allowing randomness, this could also be what is also called Merlin-Author proof system, but let's ignore that. We are gone into sort of the introduction. So let's just look at a few examples. What we want to check in all of these cases, our main goal is sort of to make, the goal in all of these is to make the task of the verifier as efficient or simple as possible. And we'll define these notions as we go on. So what could be examples of some such tasks? I'm just going to recall some classical NP problems and says examples of theorem proofs. So, by the way, I'm going to be using the word theorem and task sort of equivalently. Task is something to be accomplished. You have a particular task, and also theorem is going to use these sort of this one and write down what are the proof of this one. For example, I could ask is, I give you two numbers. 3 numbers a, b, c, 3 integers a, b, c, positive integers. Of bit length n, and ask if a has a divisor. So let's assume b is less than or equal to c. A has a divisor in between b and c. This is one such. This one does this one. This is a hard computational task. It's hard for any weak computational model to sort of do this sort of model. But of course, the clear answer is a proof for this is actually provide a divisor d. That's one proof. The task could say yes or no, and then could provide divisor d. Task is you want to solve a linear programming problem. That is, you want to say maximize A transpose X subject to some constraints. And this is an expensive one set of proof. There are several proofs here. One is it's a problem solvable in P. Interior point method sort of solve this, and the prover, an expensive prover, could solve it, send it across, and give the entire computation history of the computation tableau, or this one, of the solution as proof. See, it could give you the solution and also the whole computational history, so you to check that this is a valid proof. And then, of course, there are the classical NP complete problems. There's you're given phi is, say, some 3-sat instance, say of the form x1 or x5, or x8, x9, x10, so on. And you're asking, is this satisfiable? And the proof here is a satisfying assignment. You're all familiar with this. I'll put in one more thing. Then there's a classical case of 3 coloring. You're given a graph G. You want to ask, is it 3 colorable? And the proof here will be some coloring of the vertices, which is a valid 3 coloring.
What happens when the answer is no?
So this was, we'll have to, I'm going to talk about, so in all of these cases, in the S, we're talking about this sort of theorem. What we want, you're asking is what's the completeness and soundness of, we're talking of a underlying proof system. So we want to say if the answer is yes, there must be a proof that convinces you this one. If the answer is no, no matter what proof you give you should never be able to be convinced that the answer is this one. So all of these have this one-sided feature. There might be problems which have both proof of membership as well as proof of non-membership, both in the yes and no case. But we'll be talking about proof systems. I'm going to just write that down. So what is it in all of these? There's an underlying proof system going on here. So there's this theorem X or theorem T that I want to check whether it's true or false as this task has been accomplished. So the verifier. So what the prover is publishing is he's publishing a proof pi. And the prover is theorem verifier reads the theorem and the proof pi. At the end of it says accept or reject. This is the classical notion of, it's a sort of, we have a deterministic verifier. And what do we want of this? We want the following two features. What I'm going to call completeness is if theorem is true, then there must exist a pi such that the verifier of T pi accepts. And soundness is if T is false, then no matter which proof you give me, the verifier should always reject. This is a sort of picture. And because we want to maintain polynomiality, we want to maintain verifier, the proof should not be any longer than if the verifier has to be efficient, the proof that is being sent back to the verifier should be just polynomially long. It can't be longer than that, because otherwise the verifier doesn't even have time to read the entire proof. So this is what we are familiar with. What we want to ask is, all that the verifier wants to know is the theorem true or false. It doesn't need to look at the entire proof to check the veracity of the theorem. It just needs this one bit of information. Has the task been accomplished correctly or not? Is the theorem true or false? It doesn't trust the person who's providing the proof, but it wants to do this task. It doesn't need to read the proof in its entirety to check whether the proof is one. So the question you're going to ask is there a much more efficient way of checking this proof? So what we'll do is we're now going to strengthen the power of the verifier. We are going to make it a little randomized. So far it's not been tossing random coins. I'm going to ask, can I give a slightly different proof? The same theorem that's being proved. Can I give a different proof for a capital pi, in which we have a verifier? At this time it's a randomized verifier. For instance, the reason I would like to ask is, in some of these cases, for example, in this case of this problem, if the case of the LP problem, if you're going to give the proof is going to be the entire computation tableau, there is no point in actually delegating the task to the prover, because essentially the only way the verifier is sort of checking is running through the whole algorithm in its entirety to check if the algorithm is run correctly. You want to somehow make the task of the verifier more efficient than actually running the entire task. So we can ask is, we're going to have a randomized verifier. We're going to ask if such a verifier is possible, which is going to potentially toss random coins, few random coins. Of course, it's going to read the theorem as before, and I mean this, it's going to read the theorem. But then, based on the theorems and the random coins, it doesn't read the proof in its entirety, but decides to probe the proof at, say, a few locations, say some 10 locations. And then, based on these locations, decides to accept whether the proof is correct or not. It would be great if we had such a prover, and this is what I'm going to call this is what I'm going to call. So, and furthermore, now given that it's randomized, I now need to check what the completeness and soundness of this system is. What do I mean by the same thing out here? If the theorem is true, then what we want is there exists a pi such that the verifier is this visible, or should I?
sliding board.
Yeah, it's a sliding board. That's true. Thanks. Point.
Many theorists in the room.
Theorem is true. We want one such proof which the prover can provide, such that the verifier, when it probes this proof, accepts with high probability. For now, as Justin had done in his case, let's say it accepts all with probability 1 in the completeness case. But in the soundness case, what we would want is, if the theorem is false, then just like out here, you can't give me any proof that is going to convince the verifier that the one, but you can't expect the probability of acceptance to be 0 over here, because you're only looking at the proof at a very few locations. So what you can ask is the following sort of, this one you want for all pi, this one, the probability that the verifier accepts, say, is less than 1/10. This 1/10 is an arbitrary number. We could just drive it down as small as possible by repeating the process several times over. This is a process. And question is, what we would like to know is, it would be amazing if every such proof can be rewritten in this form that allows for such an efficient verification. This would allow, so in other words, in order to test this whole thing, all that the verifier needs to read is just these few locations and make some predicate on it, and then accept or reject based on it. It's guaranteed of the veracity of the proof without looking at the whole proof in it. It's sort of, as long as you're willing to allow for the small amount of error. So by strengthening the verifier, from going from a deterministic verifier to a randomized verifier, we have made the task of the verifier even more simpler than ever before. So it was previously, it had to read the proof in its entirety to check if the proof is valid or not. And here you want to do this. So this is a sort of useful task to, such a thing were true, it's sort of useful to have, because whenever you have a very powerful server is sort of performing a very intensive task, it can along with it provide a proof that actually the task has been accomplished in this format. So this is not the standard proof. And you will need to read the proof only at a few locations to be guaranteed that actually the task has been performed correctly or not. So what we'd like to know is, can proofs be written this way? And in fact, what the celebrated PCP theorem from the early 90s sort of says is, this is in fact true. And I will say in what setting of parameters, how many queries, how many randomness, that is, every proof can be rewritten in a format such that it can be checked super efficiently. In fact, the number of queries is as long. So this. Theorem from the 90s, building on several work. So yes, every such proof allows for super efficient verification. And what do I mean? For every problem in NP, there exists randomized verifier B that tosses at most order log n random coins. So the number of coins made by this verifier is extremely small. It's just log n. N will always be the length of the input for me. Log n random coins. And makes just constant number of queries. You can check the proof. So it says that any such thing allows for such a super efficient verification, in which you don't need to go and read the proof in its entirety. You can read the proof at very few locations and still be guaranteed of the veracity of this one. And this whole thing is in short, succinct, written in the following fashion: NP is contained in PCP 1/110th of the log n. So we do have that every proof can be rewritten in a format that allows for super efficient verification. So is this statement sort of clear? Yeah.
So going back to that SAT example, suppose this thing wasn't satisfiable.
Yes.
Then wouldn't you need something more than no in the randomized verifier?
So in the no, we would say that most of the time. So what will happen? So if this were a 3-SAT instance or a 3-colorable instance, in the yes case, we will give something such that it's always going to pass the test. In the no case, you're going to say most of the time, 9/10 of the time, you will be, no matter what proof you give me, however the prover tries to cheat me, whichever proof you get, 9/10 of the time you'll find a local inconsistency in the proof. Notice that for a 3-SAT instance to be false, it could be false in just. So a natural local test could just be give me the satisfying assignment, pick a random clause, and go and probe the 3 variables that participate in the clause and check if that clause has been satisfied or not. But a 3-SAT could be false just because every assignment violates only one clause, not a constant fraction of clauses. Every assignment possible. So if you're allowing this to be like 1, if you allow this to be like 1 minus 1 over n, then this is almost trivially follows from the statement of from NP completeness, this one. What I'm claiming is not 1 by n, 9/10. It is actually going to 9/10 of these local views are all going to reject. So we knew that there was one rejecting view. The fact it is false means that every proof has at least one place where the proof is fallacious. And now I'm claiming that it's not just one place. This sort of error is sort of smeared across. No matter what you do, the error is sort of smeared all over the proof. 9/10 of them is you're going to catch the error. Which answers? Yeah. And okay, so what are some features of this one? So let's actually just remark a few things on this before. Few things that will be important for us is, this is great that you can, every proof that was written in the classical NP way has now another proof now which allows for the super efficient verification. What we could ask is this, certainly now question is, how easy is it to do this transformation? The prover who managed to do this computation and got this proof, can he find this rewritten proof? So we would be interested in the following features, that is the prover overhead. No, even before that, what I want to ask is, you want to say that the new proof is not too long compared to the old proof. So only polynomial or even polynomially long, or even almost linear. That's one thing which we want. Other thing we want is the prover overhead in rewriting proof. And the thing which I'm not sure you'll see later on is the verifier running time. Verifier, you said it's super efficient in the terms of the number of locations it's going to probe in the proof, but we can also ask how much running time it's going to take to then first decide to accept or reject. So we could ask all of these. If all of these are in our favor, then this forms an excellent way of rewriting every proof. That is, you have a huge task, you give a proof of the task being accomplished, and you can sort of allow for extremely efficient verification stuff. Okay.
No, if the prover needs to find a given NP-complete problem, it gives me subproblem that claims equivalent. The computer, and suppose that it's true, the computation that he needs to do in order to find the subproblem that is equivalent is not counted?
No. So I didn't follow the question. There are two things out here. One is whether the amount of time for the prover to solve the original task. So let's assume you're working with 3-SAT itself. Or you're asking the reduction to 3-SAT.
Yeah, to reduction to 3-SAT. This is something that...
This is something both parties, verifier and this one, we assume can do it of their own. But in some of the applications later on, which I'll see, we'll actually do it problem specific. We will not do the reduction to 3-SAT. We will take the particular problem and actually construct the PCP for the specific problem in hand. But what I'm not counting is how much time the prover actually got to get the original proof. The original proof is just, I'm only asking how much time it's going to take to rewrite the original proof, given the proof. So this possibly it has to do an exponential search to search for this. Or if this was not such an expensive task, it was a polynomial task, then it manages to get this, and then you're asking about the overhead time. So this one is not talking about amount of time in computing the proof, but only the further overhead. Given the old proof, how much extra time does it take to convert it into this new proof? Now, why is such a statement interesting? First, of course, it's mathematically extremely interesting. It says any paper of ours can be rewritten in such a way such that the reviewer's job becomes trivial. They just need to look at 10 locations or 100 locations in the proof, and they'll be guaranteed of this one. So all papers can be rewritten in this format, this way, so that it can make the task of it sort of says the hard part of coming up proof is the coming up of the proof, and the verification is super easy. It's what you always thought the reviewing process is easier than the computing process, and this says it's not just easy, it's super easy. You can make the number of probes into the proof as small as you want. In fact, what we know today is this: if you're looking at the bits, if this is going to be over bits, and if you want this number to be half, this number can be made as small as 3. You can just look at the proof at 3 bits just look at 3 bits and be convinced of the veracity of the proof.
This application, I've heard it also before, but it seems it doesn't, so the verification time still could be large as it.
Yeah, so I haven't said what is the running time of the verifier. The verifier makes 3 probes, but I need to compare it with how much, we will come to this. This is something I will spend a fair amount at the end of my talk, ask how much time does the verifier take. So the verifier, we want it to be efficient. We certainly want it to be more efficient than the deterministic verifier. And then we will relate it to it. How much time? So certainly it has to read the theorem. So at least it has to be linear in n. But then we'll ask what's the extra amount of time. Here it not only had to read the theorem, it also had to read the proof. And so sort of if the proof was of length L, the old thing was at least linear in n and L. We would expect this to be linear in n, but have a much better dependence on L. For instance, we will later show that you can actually get the dependence on L to be polylog L. So it's going to be significantly better than this verifier. This verifier ran in poly time in L to verify this proof. This one is going to run only in polylog L time. So in that sense, it's a verifier. It's not going to be constant because of the query complexity. It needs to do some task to figure out which are the 10 queries or 100 queries it's going to make into the. So this is a task we will come to when we will see. I will outline some constructions of PCPs, and when we see that, we will see where the verifier running time is going to arise. Yeah. So what are the implications of this? It's a one, of course, it's extremely. It says that every proof, there is a new way of rewriting every proof. It's an interesting statement. Two, of course, what we've seen, it allows for efficient verification, which is the thing interesting to us. Another application which we will not go into is, this is intimately related to hardness of approximation algorithms. Just say one or two sentences, just like the theory of NP completeness talked about, showed this whole bunch of combinatorial problems are all equally hard, or this one. What this one states, the very fact that such a proof exists, that a proof can be rewritten this way, will have immediate implications to show that several of these combinatorial optimization problems are even hard to approximate in the worst case. Question? Yeah, but this is not it's a topic of requiring our own. This is not something we will go into. This is the fact that these rewriting of proofs allow for such efficient verification is what is our most interesting aspect for us, this one. So what we'll see is what actually goes into this rewriting of a proof. How do we take such a proof and massage it to rewrite it into such a proof which can be checked super efficiently. So what I will do is sort of the remaining 90 minutes or so is sort of going to, or at least 60 minutes of the 90 minutes, go into a bird's eye overview of the proof of this PCP theorem. What goes into, how do we take any proof and transform it into a fashion such that you can check it super efficiently in this fashion by looking at the new proof at just a few locations. So is the statement of what is the PCP theorem and what is it clear? Or any questions on this? So we're going to show how anything that has a usual classical proof in the NP sense, or any proof, that is you have a particular task to be accomplished, somebody performs the task and gives you a proof that the task has been accomplished, and now I want to check, all I need to check is this task has been accomplished, so I need to read the task, but I don't care about what is actually written in this. So is there a way of rewriting it such that I can be convinced that this proof is a valid proof for the theorem over there without reading all of the proof? And it says that any such proof can be rewritten in such a way as long as we allow the verifier a few extra random coins, that is log n random coins, and you strengthen the verifier this way and make the verifier, allow the verifier only to read at a few locations, say 100 locations into the proof. So how can such a thing be done? So they've actually already noticed there are, this was to Srini's question, I mean, such a transformation requires two things. One is locality of error. That is, every false proof must be false. You must be, so what I'm claiming over here is no matter what proof you give me, there must be some, at least 9/10 of the location should find a proof. That means every false proof, every fallacious proof should have very local errors. There should be 100 places. If you look at that 100, just looking at that 100 places, you should be able to detect this proof as false. Of course, where the 100 places are could be hard, but you must have this locality of error. Every false proof must have some local error.
Does the PCP theorem say anything about the computational cost of checking? It might be 100 queries, but it might take a very long time.
So this is what I meant by the verifier running time. The question is, we will ask, we would, for the applications, at least for this one, we would want the verifier's running time also to be stated. The way I have stated the PCP theorem, only set the number of queries. What we would see later on is the verifier's running time will be significantly smaller than the running time of this verifier. This verifier takes time at least linear in L, the length of this proof. This verifier will sort of, we will eventually see they can construct verifiers in which the verifier runs in time only polylog L. Though it might make 100 queries, but it would need some amount of time, it will be polylog L, and we'll see this later on.
How are you defining locality?
Locality is just them. So for example, if you're given a 3-sat instance, the fact that it is unsatisfiable means that there is some 3 variables and a particular clause that has been violated. No matter which assignment you give me, there will be some clause of size 3 in which local. So there is locality. I'm just talking about here. If the query complex is 100, there must be some 100 locations in the proof, which if you look at that 100 locations, you already know for every proof there must be at least 100 locations where if you just look at that 100 locations, you're able to detect that the proof is fallacious. This is not a very surprising thing. The fact that 3-sat is NP complete already tells you that 3-sat is NP complete or graph coloring is NP complete, tells you that every false proof will have some very local errors. That is, the fact that graph coloring is NP complete, you can transform every statement into graph coloring and give a proof of the coloring statement. Give me a 3 coloring of it. So if it's not a valid 3 coloring, there exists a particular edge that is not satisfied. So there's a locality of 2 over there. So this is not the very surprising fact. It's fact that there's an abundance of local errors. This is the most surprising aspect of it. That is, all that we were able to guarantee previously that there was just one local error, and now we're going to say that it's not one local error. This error over here in the original thing, this proof could have been just false because of some 3 locations not satisfying a property. When you rewrite it this way, it's stating that you sort of smearing this error all over the place. So we want this proof writing to have this extra feature. At first, locality of error, this is something which we know how to do. Just NP completeness of 3-sat and graph coloring will give you this. But furthermore, we want to do this in such that the errors are smeared across all. That is, you can never have one error in it. If a proof is false, it should have abundant errors all over the place. You see? Yeah.
In the morning, we had this blowing up. If there is a discrepancy, it blows up all over the place.
Yes. So exactly.
All over the place, it has also the locality property, or just a fraction.
So it didn't have the locality property. So yeah. So I was just going to come to the thing. This morning we saw if you had 2 polynomials, if we saw that if they disagree with each other, if they agree with each other, they agree everywhere. But if they disagree with each other, then they disagree almost everywhere. It is sort of, and if you could somehow put this disagreement into this errors into these sort of disagreements, we would be able to capture them. So Morning sort of says we can use polynomials, but the question is, are these things also locally testable? We'll come to this extra feature. So we will be using what Justin built in the morning, that is usually in particular, we'll be using the Schwarz-Zippel lemma over and over again, stating that if 2 polynomials are distinct, if 2 low-degree polynomials are distinct, then actually they will disagree almost everywhere, this one. And we'll use that feature to actually take the errors and sort of say if there's a false proof, fact it's false, it must be the fact that it is false. The errors are there all over the place. It's not just at one location. We're going to use this, but we need an extra feature about, by the way, I should remark something about what Justin said morning. So talked about polynomials having this property. It's not just polynomials that have this property. Any error correcting code has this property. You take a code, you take any object and you encode it. Once you encode it, 2 messages, if they are distinct, the corresponding encoded messages are going to be distinct almost everywhere. That's the property of error correcting codes. And in fact, some of the proofs in the statement, but it's not, some of the things which we did in the morning could be, for example, the equality protocol, we could replace it by not just with, take the Reed-Solomon code word, but with any code word, and we could have redone the proof. But both the IP equals P space and this, it needs a little more properties of polynomials than just the fact it's a code. And we will see some more I'll mention in detail some properties of polynomials that we will need to actually get these two features. So what I will try to do in this one is we're going to try to sort of give a sketch of this proof, but we will do it in two parts. Firstly, I will sort of sketch a proof in which even this should be surprising. I'll say that any proof, you can rewrite it in an exponentially long fashion such that it is now testable with, say, looking at it at 15 queries. Even this fact that you can check a proof here, the PCP theorem says that this rewriting can be done with just a polynomial overhead. I'll say let's weaken on this one. I will rewrite this proof exponentially longer, but say that in spite of it, this verifier is allowed to read this proof only at a constant number of locations. We'll start off with this. We'll show a baby case problem. We'll show that you can get a sort of a PCP theorem in which the proof length blows up exponentially, but yet the checking becomes constant. You don't have to read the entire proof. You can read the proof only at, say, 10 locations and be convinced of the veracity of the proof. And then later on, we'll see that some of ideas can be here further pushed to actually get polynomial sized proofs in which the number of queries is much smaller. By the way, I should mention two things. So currently, for the proof of the PCP theorem, the proofs of PCP theorem, we note two types of proofs of PCP theorem. There are two types of proofs. One is the algebraic proof, which is the one I'll be following or outlining in this one. This is from the original work of AS, ALMSs. Stuff along the lines of what Justin had talked about. It is a proof which uses polynomials. This one, actually the proof I'll be giving is actually not the original proof, but with several subsequent improvements that happened in the decades thereafter. But today we actually know another proof of the PCP theorem, which is a combinatorial proof, which has a really combinatorial proof due to Irid Dinur from 2006. This is not a proof which I'll become. We'll look at the algebraic proof of this. And in the warm-up, we'll sort of construct exponential sized.
Well, can I ask something? So for the combinatorial proofs, is there any work that tries to kind of concretize this?
Concretize what?
So in the algebraic proofs, given the subject of this semester also, people have been trying to use the ideas, context of, blockchains or things like that. Does anybody look at a combinatorial proof to try to look at what the constants are?
No, so the combinatorial proof has a slight disadvantage to it. The algebraic proofs sort of scale up. So there's a way in which it can be done. That's the question of the verifier running time. It runs in log L. So the question is what's the verifier running time in terms of the original proof length? If the original proof length is L, the algebraic proofs can be written in such a way that the verifier runs in time just poly log L. And this is useful when you want to sort of scale this up to MIP equals next per any such thing. The combinatorial proof does not have this flavor. It runs in poly L.
So there's an open problem there.
So there is, so it is conceivable that can, so the way we know how to make it is use some extra algebraic constructions into it to make it this one. If we don't have a fully combinatorial, which has this, which is useful for the verification purposes.
That's even true for using combinatorial type proof for specific statements, not a generic.
I don't think that's
Anybody looked at it?
I don't think that's true. For general NP, this combinatorial Dinur's proof has this problem that it doesn't scale up. For example, it will not give a proof.
The problem is combinatorial in nature, like counting triangles.
It's conceivable. It's feasible. It's
expresses an algebraic expression.
feasible. I don't think anybody has looked at it from that angle. So, yeah.
Well, see, is it just the issue of the input length? Because in many of the cases, the input is short, the witness is very long.
It's not in case of the input length. You want the verifier to be efficient. Verifier is going to run at least, it has to read the input once, so it's going to be at least linear in n. But the question is what its dependence on L is. And the combinatorial proofs all have the flavor that they are poly in L. Whereas in order to do the scaling up, you want them to be poly in logarithm log of L.
L is what?
L is the length of the length of the proof, the witness length.
I see.
Yeah.
So,
Prahladh, when you say fully combinatorial, I mean, I know that it's not well defined, but you still use some finite gadget, and can you instantiate it? Again, it's not clear if addition is combinatorics or other.
Yeah. So all I can say is this one uses polynomials, this does not use polynomials. So, with notion of what is algebraic combinatorial is a because this also is going to use.
The question is that you start with a finite gadget. So
it is a gadget. It's sort of a gadget based.
To instantiate the finite gadget, I mean, you needed the basis of the recursion something, right? So
they use an expander. So it's sort of going to. So the combinatorial proof has this flavor that it's not one single reduction. There's a reduction. Each reduction is used based on an expander graph, and there are log n such. But it's each one.
From a Ritz proof that you need to bootstrap, you need to start with some finite proof, and you say, okay, use either LMS or a computer search because it's finite. And my question is whether there is an explicit basis for this.
She'll have to start off with an expander on a constant size thing which has properties. So you just do a brute force search, or you pick up one of these.
But to prove the existence of such an object, either brute force or.
So for the probabilistic method, yeah, you pull out one such thing from there. Yeah. No, in that sense, there is no algebraic flavor to them. They have expander graphs going on all over them, but they don't have a algebraic flavor. There is a search for an expander that happens, a constant size expander, which one either does by brute force or resorts to the expander graphs coming out of planes and lines, which are algebraic based expanders. Okay. Start off this sort of problem, an exponential size. So this is not what we wanted to do, but yet constant query. TCP for n. I'm going to sort of prove this. Let's actually even take the problem which I will work with. It could work with. The work is you're given a system of quadratic equations. The question we're going to ask is, given a system of quadratic equations, so basically I'm looking at equations of the form summation aij xi xj equals sum b. I'm given several such equations. I want to ask, is there a Boolean setting for the variables xi that simultaneously satisfies it? Are they simultaneously satisfiable? This is an NP-complete problem. That is, you have, so I'm going to give a bunch of quadratic equations, something of the form, say x1, x2 plus x3, x4 plus x6 equals 8. Several of such equations, say m such equations. And we'll ask, is there a Boolean? And let's assume all simultaneously, I'm assuming everything is happening over 0, 1. All the constants are from 0, 1. And I'm asking, is there a common setting? Is there a setting to the variables x that satisfies them completely? Simultaneously, this is an NP-complete problem. So, of course, a proof for this, the classical NP proof of this will be the assignment, x itself. You give me x, and then the verifier just plugs in those x variables into each of the quadratic equations and checks if those equations are satisfied. This will be the classical deterministic verifier. What I want to write is now, instead of giving this x as proof, we'll give a different proof such that this proof can be checked by the verifier significantly by looking at the proof at very few locations, say just 10 locations or 12 locations of the proof. The caveat will be this proof will be much longer, it will be exponentially long. But even then, it's quite a surprising fact that you can be convinced that the set of quadratic equations are verifiable by looking at a proof, even though exponentially long, but only a constant number of locations. And actually, we'll make a problem life a little more easier. We'll actually going to make it, and then we'll initially make it just a bunch of linear equations. So the input is just, let's say, why is this the input is just going to be things of the form a1x equals b1, a2x equals b2. Shorthand for just this notation, ai xi from 1 to n. All these are n-bit vectors, and x is also an n-bit vector. All the bi's are bits. The last input is this. And the question is it simultaneously? Of course, this is an easy problem. It's just solving a linear system, and we can solve this easily. It's just solving this a linear system of equations, and of course, we know how to solve this one. What we'll show firstly, we'll give a proof for this. We'll give an exponential proof, but even there, actually, it will be non-trivial. In fact, the usual any proof that we know how to solve this requires time at least n square. I can't think of anything at least time mn. It has to look at the whole input. What we will give is we'll give a proof which just requires in which the verifier runs only in time linear in n, not sort of mn, though it looks at an exponential response. So even in this case, actually we'll be doing something non-trivial. This is a simple case for which the verifier doesn't need the help of a prover to do this task. It's a fairly simple task, solving a system of linear equations. We will show how to give an exponentially long proof. One proof for this is just give me all the x's, and then you can check that the equations are satisfied. We'll instead of giving this, we'll give the x's in a different fashion. We'll write the x proof in a different fashion that will convince me that they are simultaneously satisfiable. And then we'll extend it, time permitting, I'll show how to extend this to quadratic equations. So is it setting clear? What to do? So we have, this is the input we are given to us. We are given a bunch of linear equations, and we want to ask, is it simultaneously satisfiable? So the classical NP witness for this, you don't need NP and all for this, is just the x that satisfies it. X that satisfies all the equations. Now instead of x, we are going to give some, so the new PCP proof is going to be some encoding of x that allows for efficient verification, efficient local verification. I'll introduce what is this encoding, and then we'll go into the trying to prove what it is in the next half of the. So sort of we'll be using this fact which Justin had mentioned in the morning repeatedly over, what's called the Schwartz-Zippel lemma. The polynomial f is a finite field is Q. This is of degree less than or equal to D. Let P and Q be two polynomials of this one. Then at a rand, if P not equal to Q, if they are not identical polynomials, then we are in fact equal at very few locations. In fact, at most locations they are going to be distinct. We are going to be using this over and over again. In fact, we'll be using the multivariate version of this. That is, these are the alpha is. This was not something with Justin. He mentioned this in passing. That is, even the multivariate version of this theorem. This is what's called in the morning proof of the sum check protocol. We used only the univariate version of it, which is fairly easy to see. The multivariate version requires it's easy, but it's a non-trivial proof. And this is what we'll be using. In fact, we will be using it for this case, just for the case D equals 1. We'll just set D equals 1. So the encoding we're going to give is what is called the Hadamard encoding. So we're going to encode X, an n-bit string, with a 2 to the n-bit string. And what is it that we're going to do? We're going to map X to its inner product with every possible Y, every possible other inner. We're going to use this encoding. So instead of providing X, we are going to give us proof this encoding, which is a 2 to the n long string, and show that this string is going to enable us to do this checking extremely efficiently. So the PCP proof will in fact be the Hadamard encoding of X. This is what the honest prover will give you. A dishonest prover could give you something else, and we'll say that no matter what he does, the verifier will be robust so that if there is no X that satisfies it, he will catch it in a constant by looking at the proof only at a constant number of locations, and most of the time. That is, you're going to give this function f. So we'll view this whole thing as this function L of x, which maps n-bit strings to 0, 1. This is it's mapping a y to inner product. And what we show after the break is this proof, though exponentially long, it blows up the original proof of length n into an exponentially long this one. It is actually extremely efficiently checkable. And all we'll use is the Schwarz-Zippel lemma for d equals 1 to prove this. A good point to break. Let's